All right, you are back with me. We are reading Python Programming, An Introduction to Computer Science, the third edition by John Zelle. And we are in Chapter 11 in this video, and the title of Chapter 11 is Data Collections. We have objectives for this chapter. Number 1, to understand and use lists or arrays to represent a collection of related data. Next, to be familiar with the functions and methods available for manipulating Python lists. Next, to be able to write programs that use lists to manage a collection of information. Then, to be able to write programs that use lists and classes to structure complex data. And finally, to understand the use of Python dictionaries for storing non-sequential collections. I hope this chapter is shorter. You're so long. All right, so section 11.1, example problem, simple statistics. Statistics are never simple. As you saw in the last chapter, classes are one mechanism for structuring the data in our programs. Classes alone, however, are not enough to satisfy all our data handling needs. If you think about the kinds of data that most real-world programs manipulate, you will quickly realize that many programs deal with large collections of similar information. A few examples of the collections that you might find in a modern program include words in a document, students in a course, data from an experiment, customers of a business, graphics, objects drawn on the screen, cards in a deck. In this chapter, you will learn techniques for writing programs that manipulate collections like these. Let's start with a simple example, a collection of numbers. Back in Chapter 8, we wrote a simple but useful program to compute the mean or the average of a set of numbers entered by the user. Just to refresh your memory, as if you could forget it, here is the program again. He said he wouldn't. Here we go. Hashtag average4.py. Def main empty parentheses colon new line total equals 0.0 new line count equals 0 new line x capital STR equals input open parentheses open quote enter a number open parentheses enter key to quit end parentheses arrow arrow end quote end parentheses new line while x capital STR exclamation point equals empty quotes colon new line x equals float open parentheses x capital STR end parentheses new line total equals total plus x new line count equals count plus 1 new line x capital STR equals input open parentheses open quote enter a number open parentheses enter key to quit end parentheses arrow arrow end quote end parentheses new line print open parentheses quote backslash n the average of the numbers is end quote comma total divided by count end parentheses new line main empty parentheses. This program allows the user to enter a sequence of numbers, but the program itself does not keep track of what numbers were entered. Instead, it just keeps a summary of the numbers in the form of a running total. That's all that's needed to compute the mean. Suppose we want to extend this program so that it computes not only the mean, but two other standard statistical measures, the median and standard deviation of the data. You are probably familiar with the concept of a median. That is the value that splits the data set into equal-sized parts. For the data 2, 4, 6, 9, and 13, the median value is 6, since there are two values greater than 6 and two that are smaller. One way to calculate the median is to store all the numbers and put them in order so that we can identify the middle value. The standard deviation is a measure of how spread out the data is relative to the mean. If the data is tightly clustered around the mean, then the standard deviation is small. When the data is more spread out, the standard deviation is larger. The standard deviation provides a yardstick for determining how exceptional a value is. For example, some teachers define capital A, or an A, as any score that is at least 2 standard deviations above the mean or average. The standard deviation S is defined in this formula. S equals the square root of sigma times, in parentheses, x with a line over it minus x with an I next to it, and parentheses, squared over n minus 1. In this formula, x with the line over it is the mean, and x with the I next to it represents the ith number data value, and n is the number of data values. The formula looks complicated, but it is not hard to compute. The expression x with a line over it minus x with an I next to it squared is the square of the deviation of an individual item from the mean. The numerator of the fraction is the sum of the deviations squared across all the data values. Let's take a simple example. If we again use the values 2, 4, 6, 9, and 13, the mean of this data, the x with the line over it, is 6.8. So the numerator of the fraction is computed as this: 6.8 minus 2 squared plus 6.8 minus 4 squared plus 6.8 minus 6 squared plus 6.8 minus 9 squared plus 6.8 minus 13 squared equals 74.8. Finishing out the calculations gives us S equals the square root of 74.8 divided by 5 minus 1, which is equal to the square root of 18.7, which is equal to 4.32. The standard deviation is about 4.3. You can see how the first step of this calculation uses both the mean, which can't be computed until all of the numbers have been entered, and each individual value as well. Computing the standard deviation this way requires some method to remember all of the individual values that were entered. Section 11.2, Applying Lists. In order to complete our enhanced statistics program, we need a way to store and manipulate the entire collection of numbers. We can't just use a bunch of independent variables because we don't know how many numbers there will be. What we need is some way of combining an entire collection of values into one object. Actually, we've already done something like this, but we haven't discussed all of the details. Take a look at these interactive examples. Arrows, list, open parentheses, range, 10 in parentheses, end parentheses, new line, in brackets, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, end brackets. New line, arrows, quote, this is an X parrot, exclamation point, end quote, dot, split, empty parentheses, new line, bracket, quote, single quote, this, single quote, comma, single quote is, single quote, comma, single quote, an, single quote, comma, single quote, X parrot, exclamation point, apostrophe, single quote, and bracket. Now I'm confused about whether it's an apostrophe or a single quote. Both of these familiar functions return a collection of values denoted by the enclosing square brackets. These are lists, of course. So someone tell me, is that supposed to be apostrophe this, apostrophe? Or is it single quote this, single quote? You tell me. All right, the next section, 11.2.1, lists and arrays. As you know, Python lists are ordered sequences of items. In fact, the ideas and notations that we use for manipulating lists are borrowed from the mathematical notion of sequence. Mathematicians sometimes give an entire sequence of items a single name. For instance, a sequence of n numbers might just be called capital S. Capital S equals S0, S1, S2, S3, capital Sn minus 1. When they want to refer to specific values in the sequence, these values are denoted by subscripts. In this example, the first item in the sequence is denoted with the subscript 0, S0. By using numbers as subscripts, mathematicians are able to succinctly summarize computations over items in the sequence using subscript variables. For example, the sum of the above sequence is written using standard summation notation as, I'm going to show you this. This is the mathematical notation, and what we have there is n minus 1 over sigma over I minus 0 times Si, capital Si. A similar idea can be applied to computer programs. With a list, we can use a single variable to represent an entire sequence, and the individual items in the sequence can be accessed through subscripting. Well, almost. We don't have a way of typing subscripts, but we use indexing instead. Suppose that our sequence is stored in a variable called little s. We could write a loop to calculate the sum of the items in the sequence like this. Total equals 0. New line, for I in range, n in parentheses, colon. New line, total minus total plus s, and then an I in brackets. Virtually all computer languages provide some sort of sequence structure similar to Python's list. In other languages, it is called an array. To summarize, a list or array is a sequence of items. To summarize, a list or array is a sequence of items where the entire sequence is referred to by a single name, in this case, little s, and individual items can be selected by indexing, for example, Si in brackets. Arrays in other programming languages are generally fixed size. When you create an array, you have to specify how many items it will hold. If you don't know how many items you will have, then you have to allocate a large array, just in case, and keep track of how many slots you actually fill. Arrays are also usually homogeneous. That means they are restricted to holding objects of a single data type. You can have an array of ints or an array of strings, but you cannot mix strings and ints in a single array. In contrast, Python lists are dynamic. They can grow and shrink on demand. They also are heterogeneous. You can mix arbitrary data types in a single list. In a nutshell, Python lists are mutable sequences of arbitrary objects. Section 11.2.2, list operations. Because lists are sequences, you know that all of the Python built-in sequence operations also apply to lists. To jog your memory, here is a summary of those operations. The operator seek plus seek is meaning a concatenation. So using the plus sign in between can connect to elements to whatever. So you have a sequence, then you have the asterisks, then you have an integer expression, so then you have a number of repetitions. If you have a sequence and then you have something in brackets, the meaning is indexing. If you have len and then you have the sequence command inside of parentheses, then you have a length. If you have sequence and you have brackets with a colon inside, then you have slicing. If you have a for and a variable, an in and a sequence, you have the meaning of that is an iteration. And if you have an expression in a sequence, then you have membership check and returns a Boolean value. Except for the last, membership check, these are the same operations that we used before on strings. The membership operation can be used to see if a certain value appears anywhere in a sequence. Here are a couple of quick examples checking for membership in lists and strings. Before we do that, I'm going to show you the chart that I just read. Hopefully that was clear on what those operators are and what they do. What do they mean in Python? All right, so lists and strings, checking for membership, new page. Arrows, first equals in brackets 1, 2, 3, 4. Next line, arrows, 3 in first. New line, capital T, true. New line, arrows, 5 in first. New line, capital F, false. New line, arrows, ands equals single quote Y single quote. New line, arrows, ands in single quotes, capital Y, lowercase y. New line, capital T, true. By the way, since we can iterate through lists, the summing example from above can be written more simply and clearly this way. Total equals 0. For x in s colon, new line, total equals total plus x. Recall that one important difference between lists and strings is that lists are mutable. You can use assignment to change the value of items in a list. Here's an example. Arrows, first equals in brackets 1, 2, 3, 4. New line, arrows, first in brackets 3, new line 4. New line, arrows, first in brackets 3 equals in quotes hello. New line, arrows, first, new line, bracket 1, 2, 3, in single quotes hello and bracket. New line, arrows, first in brackets 2 equals 7. New line, arrows, first. New line in brackets 1, 2, 7, in single quotes hello and bracket. New line, arrows, first in brackets 1, 3 equals in brackets quote unquote slice, quote unquote assignment, end brackets. New line, arrows, first. New line in bracket, start bracket 1, single quote slice, single quote assignment, single quote hello, end bracket. As the last example shows, it's even possible to change an entire subsequence in a list by assigning a list into a slice. Python lists are very flexible. Don't attempt this in other languages. As you know, lists can be created by listing items inside square brackets. Odds equals in brackets 1, 3, 5, 7, 9, and brackets. New line, food equals open brackets, quote unquote spam, quote unquote eggs, quote unquote back bacon, and brackets. New line, silly equals open brackets 1, quote unquote spam, 4, quote unquote you, and brackets. New line, empty equals empty brackets. In the last example, empty is a list containing no items at all, an empty list. A list of identical items can be created using the repetition operator. This example creates a list containing 50 zeros. Zeros equals 0 in brackets and the multiply sign, the asterisks, 50. As we discussed in Chapter 5, lists are often built up one piece at a time using the append method. Here is a fragment of code that fills a list with positive numbers typed by the user. Nums equal empty brackets, new line x equals float, open parentheses, input, open parentheses, in single quotes, enter a number colon, end parentheses, new line, while x greater than or equal to 0, colon, new line, nums dot append, and open parentheses, x, close parentheses, new line, x equals float, open parentheses, input, open parentheses, open quote, enter a number, colon, end parentheses, end quote, end parentheses, end parentheses. In essence, nums is being used as an accumulator. The accumulator starts out empty, and each time through the loop, a new value is tacked on. The append method is just one example of a number of useful list-specific methods. This table briefly summarizes some things you can do to a list. So I'm going to show you that graph thing here. Useful information. Please take some time to look at that in your book, in your copy. So we have list.append x, and that means that adds element x to the end of the list. We have list.sort with empty parentheses, and that orders the list. And we have list.reverse empty parentheses, and that reverses the list. We have list.index with an x inside the parentheses, and that returns index of the first occurrence of x. That sounds useful. We have list.insert, and then inside parentheses we have I, x, and that inserts x into the list at index I. We have list.count with x in parentheses, returns the number of occurrences of x in the list. Now we have list.remove x inside parentheses, that deletes the first occurrence of x in the list. And finally, list.pop with an I in parentheses, deletes the ith element of the list and returns its value. We have seen how lists can grow by appending new items. Lists can also shrink when items are deleted. Individual items or entire slices can be removed from a list using the del operator. Arrows, my capital L list, new line, bracket, 34, 26, 0, 10, and brackets. New line, arrows, del, my list, 1 in brackets. New line, arrows, my list, new line in brackets, 34, 0, 10, no comma. New line, arrows, del, my list, in brackets, 1, 3, end brackets, new line, arrows, my list, new line in brackets, 34. Notice that del is not a list method, but a built-in operation that can be used on list items. As you can see, Python lists provide a very flexible mechanism for handling arbitrarily large sequences of data. Using lists is easy if you keep these basic principles in mind. First, a list is a sequence of items stored as a single object. Next, items in a list can be accessed by indexing, and sublists can be accessed by slicing. Next, lists are mutable. Individual items or entire slices can be replaced through assignment statements. Next, lists support a number of convenient and frequently used methods. And finally, lists will grow and shrink as needed. All right, section 11.2.3, statistics with lists. Now that you know more about lists, we are ready to solve our little statistics problem. Recall that we are trying to develop a program that can compute the mean, median, and standard deviation of a sequence of numbers entered by the user. One obvious way to approach this problem is to store the numbers in a list. We can write a series of functions, mean, standard deviation, and median, that take a list of numbers and calculate the corresponding statistics. Let's start by using lists to rewrite our original program that only computes the mean. First, we need a function that gets the numbers from the user. Let's call it getNumbers. This function will implement the basic sentinel loop from our original program to input a sequence of numbers. We will use an initially empty list as an accumulator to collect the numbers. The list will then be returned from the function. Here's the code for getNumbers. New line, def, getNumbers, empty parentheses, colon, new line, nums equal empty brackets, hashtag start with an empty list, hashtag new line, hashtag sentinel loop to get numbers, new line, x capital STR equals input, open parentheses, open quote, enter a number, open parentheses, enter to quit, end parentheses, arrow, arrow, end quote, end parentheses, new line, while x capital STR, exclamation point equals empty quotes, colon, new line, x equals float, in parentheses, x capital STR, new line, nums dot append x in parentheses, hashtag add this value to the list. New line, x capital STR equals input, open parentheses, open quote, enter a number, in parentheses, enter to quit, end parentheses, arrow, arrow, end quote, end parentheses, new line, return nums. Using this function, we can get a list of numbers from the user with a single line of code. Data equals get numbers, empty parentheses. New line. Next, let's implement a function that computes the mean of the numbers in a list. This function takes a list of numbers as a parameter and returns the mean. We will use a loop to go through the list and compute the sum. New line, def, mean, nums in parentheses, colon, new line, total equals 0.0, new line for num in nums, colon, new line, total equals total plus num, new line, return total divided by len, nums in parentheses. Notice how the average is computed and returned in the last line of this function. The len operation returns the length of a list. We don't need a separate loop accumulator to determine how many numbers there are. That's nice. With these two functions, our original program to average a series of numbers can now be done in two simple lines. Def main empty parentheses, colon, new line, data equals get numbers, empty parentheses, new line, print, open parentheses, single quote, the mean is, end quote, comma, mean, open parentheses, data, close parentheses, close parentheses. Next, let's tackle the standard deviation function, or STD, capital DEV, for standard deviation. In order, use the standard deviation. I think there's a typo. In order to use the standard deviation formula discussed above, we first need to compute the mean. We have a design choice here. The value of the mean can either be calculated inside standard dev or passed to the function as a parameter. Which way should we do it? On the one hand, calculating the mean inside standard dev seems cleaner, as it makes the interface with the function simpler. To get the standard deviation of a set of numbers, we just call standard deviation or stad dev and pass it the list of numbers. This is exactly analogous to how mean and median below works. On the other hand, programs that need to compute a standard deviation will almost certainly need to compute the mean as well. Computing it again in stad dev results in the calculations being done twice. If our data set is large, this seems inefficient. Since our program is going to output both the mean and the standard deviation, let's have the main program compute the mean and pass it as a parameter to the std_dev. Other options are explored in the exercises at the end of the chapter. Here is the code to compute the standard deviation using the mean, x bar, as a parameter. That's the x with the line on top. We have x bar, and that stands for mean or average. Okay, we have a new line, def, std_def, open parentheses, nums, comma, x bar, end parentheses, colon, new line, sumdev_squa equals 0.0, new line, for num in nums, colon, new line, dev equals x bar minus num, new line, sumdev_squa equals sumdev_squa plus dev, asterisks, dev, asterisk represents multiplication, new line, return squirt or square root, open parentheses, sumdev_squa divided by or forward slash, open parentheses, len, open parentheses, nums, close parentheses, -1, and close parentheses, close parentheses. Notice how the summation from the standard deviation formula is computed using a loop with an accumulator. The variable sumdev_squa stores the running sum of the squares of the deviations. I appreciate it doing that. Once the sum has been computed, the last line of the function calculates the rest of the formula. Yay! Finally, we come to the median function. This one is a little bit trickier as we do not have a formula to calculate the median. Boo! We need an algorithm that picks out the middle value. The first step is to arrange the numbers in increasing order. Whatever value ends up in the middle of the pack is by definition the median. There is just one small complication. If we have an even number of values, there is no exact middle number. In that case, the median number is determined by averaging the two middle values. So the median of 3, 5, 6, and 9 is 3 plus 5 divided by 2, which equals 5.5. In pseudocode, our median algorithm looks like this. Sort the numbers into ascending order. If the size of the data is odd, med equals the middle value, else med equals the average of the two middle values, return med. This algorithm translates almost directly into Python code. Yay! We can take advantage of the sort method to put the list in order. To test whether the size is even, we need to see if it is divisible by 2. This is a perfect application of the remainder operation. The size is even if size %2 equals 0. That is, dividing by 2 leaves a remainder of 0. With these insights, we are ready to write the code. Here we go. First line of code. Def, median, nums in parentheses, colon, new line, nums dot sort, empty parentheses, new line, size equals len, nums in parentheses, new line, mid-pos equals size, //2, new line, if size, %, 2 equals 0, colon, new line, med equals, open parentheses, nums, mid-pos inside brackets, plus nums, mid-pos -1 inside brackets, end parentheses, divided by 2. New line, else, colon, med equals, nums, mid-pos inside brackets, new line, return med. You should study this code carefully. Please do look at your book to be sure you understand how it selects the correct median from the sorted list. The middle position of the list is calculated using integer division as size divided by 2. If size is 3, then mid-pos, or the middle position, is 1. 2 goes into 3 just one time. This is the correct middle position since the 3 values in the list will have the indexes 0, 1, 2. Now, suppose size is 4. In this case, mid-pos, or the middle position, will be 2, and the 4 values will be in locations 0, 1, 2, 3. The correct median is found by averaging the values in mid-pos 2 and mid-pos -1, 1. Now that we have all the basic functions, finishing out the program is a cinch. So he says, whatever. So we have def main empty parentheses colon new line print open parentheses open quote. This program computes mean, comma, median, comma, and standard deviation period. End quote, end parentheses. New line. Data equals get numbers, empty parentheses. New line x bar equals mean and data in parentheses. New line std equals standard dev or stat dev open parentheses data comma x bar end parentheses. New line med equals median and data inside parentheses. New line print open parentheses open quote /n or \n the mean is end quote comma x bar end parentheses. New line print open parentheses open quote the standard deviation is end quote comma std end parentheses. New line print open parentheses open quote the median is end quote comma med end parentheses. Many computational tasks, from assigning grades to monitoring flight systems on the space shuttle, require some sort of statistical analysis. By using the if _name _= open quote single quote __ main __ end single quote technique, we might make our code useful as a standalone program and as a general statistical library module. Here's the program. #stats.py. New line from math import square root, sqrt for square root. New line def get numbers empty parentheses colon new line nums equals empty brackets. Start with an empty list. New line sentinel loop to get numbers. New line $str equals input open parentheses open quote enter a number open parentheses enter to quit end parentheses arrow end quote end parentheses. New line while $str exclamation point equals empty quotes colon new line x equals float open parentheses $str end parentheses. New line nums dot append x in parentheses add this value to the list. New line $str equals input open parentheses open quote enter a number open parentheses enter to quit end parentheses arrow end quote end parentheses. New line return nums. New line def mean open parentheses nums end parentheses colon new line total equals 0.0 new line for num in nums colon new line total equals total plus num. New line return total divided by len nums in parentheses. New line def standard deviation dev open parentheses nums comma x bar end parentheses colon new line sum dev square equals 0.0 new line for num in nums new line dev equal num minus x bar, new line sum dev squa equals sum dev squa plus dev multiplied by dev, new line return square root, open the parentheses, sum dev squa divided by new open parentheses, len, open parentheses, nums, close parentheses, -1 or -1, end parentheses, new line, def, median, nums in parentheses, colon, new line, nums dot sort, empty parentheses, new line, size equals len, nums in parentheses, new line, mid pos equals size divided by 2. New line, if size %2 equals 0, colon, new line, med equals open parentheses, nums, mid-pos in brackets, plus nums, mid-pos -1 in brackets, end parentheses, divided by 2.0. New line, else, colon, new line, med equals nums, mid-pos in brackets, new line, return med, new line, def, main, empty parentheses, colon, new line, print, open parentheses, quote, this program computes mean, comma, median, comma, and standard deviation, period, end quote, end parentheses. New line, data equals get numbers, empty parentheses. New line, x bar equals mean, data in parentheses. New line, std equals stat dev, open parentheses, data, comma, x bar, close parentheses, new line, med equals median, data inside parentheses, new line, print, open parentheses, open quote, \n, the mean is, end quote, comma, x bar, end parentheses, new line, print, open parentheses, quote, the standard deviation is, quote, comma, std, end parentheses, new line, print, parentheses, quote, the median is, end quote, comma, med, end parentheses, new line, if, name, equals, single quote, main, end single quote, colon, main, empty parentheses. Okay, you can feel free to test that. New section 11.3, lists of records. All of the list examples we've looked at so far have involved lists of simple types like numbers and strings. However, a list can be used to store collections of any type. One particularly useful application is storing a collection of records. We can illustrate this idea by building on the student GPA data processing program from the last chapter. Recall that our previous grade processing program read through a file of student grade information to find and print information about the student with the highest GPA. One of the most common operations performed in this kind of data is sorting. We might want the list in a different order for different purposes. An academic advisor might like to have a file with grade information sorted alphabetically by the name of the student. To determine which students have enough credit hours for graduation, it would be useful to have the file in order according to credit hours. And a GPA sort would be useful for deciding which students are in the top 10% of the class. Let's write a program that sorts a file of students according to their GPA. The program will make use of a list of student objects. We just need to borrow the student class from our previous program and add a bit of list processing. The basic algorithm for our program is very simple. Get the name of the input file from the user. Read student information into a list. Sort the list by GPA. Get the name of the output file from the user. Write the student information from the list into a file. Let's begin with the file processing. We want to read through the data file and create a list of students. Here's a function that takes a takes a file name as a parameter and returns a list of student objects from the file. Here we go. Def, new line, def, read students, in parentheses, file name, new line, in file equals, open, in parentheses, file name, in single quotes, R, and parentheses. New line, students equal, empty brackets. New line, for line in file, new line, students dot append, open parentheses, make student, open parentheses, line, close parentheses, new line, in file dot close, empty parentheses, new line, return students. This function first opens the file for reading and then reads line by line, appending a student object to the students list for each line of the file. Notice that I am borrowing the make student function from the GPA program. It creates a student object from a line of the file. We will have to be sure to import this function along with the student class at the top of our program. While we're thinking about files, let's also write a function that can write the list of students back out to a file. Remember, each line of the file should contain 3 pieces of information: name, credit hours, and quality points, separated by tabs. The quote to do this is straightforward. Here we go. Def, write students, in parentheses, students, file name, and parentheses, new line, hashtag, student is a list of student objects, new line, out file equals, open, and in parentheses, file name, in single quotes, W, and parentheses, new line for S in students, new line, print, open parentheses, quote, 0 in fancy brackets, I'm gonna call it, backslash T, 1 in fancy brackets, backslash T, 2 in fancy brackets, end quote, period. New line, format, open parentheses, S dot get name, empty parentheses, S dot get hours, empty parentheses, S dot get Q points, empty parentheses, end parentheses, new line file equals out file, end parentheses. I think that was the same line. It just got bumped down a line in the book. New line, out file dot close, empty parentheses. Notice that I use the string formatting method to generate the appropriate line of output. The backslash T represents a tab character. So that's what he was doing there. As backslash N is a new line function. Backslash T represents the tab function. Using the functions read students and write students, we can easily convert our data file into a list of students and then write it back out to a file. All we have to do now is figure out how to sort the records by GPA. In the statistics program, we used the sort method to sort a list of numbers. What happens if we try to sort a list that contains something other than numbers? In this case, we want to sort a list of student objects. Sorry, I need to turn off an alarm before it goes off. In this case, we want to sort a list of student objects. Let's try that out and see what happens. First line, we have arrows. First equals GPA sort dot read students, in parentheses, quote, students dot dat, end quote, end parentheses. New line, arrows first. New line, bracket, left facing arrow, GPA dot student, object at OXB7B1554C, right facing arrow, comma, left facing arrow, GPA dot student, object at 0xb7b156cc, right facing arrow, comma, left facing arrow, GPA dot student, object at 0xb7b1558c, right facing arrow, comma, left facing arrow, GPA student, object at 0xb7b155cc, right facing arrow, comma, left facing arrow, GPA student dot student, object at 0xb7b156ec, right facing arrow, end bracket. New line, arrows, first dot sort, empty parentheses. New line, trace back, open parentheses, most recent call, last, end parentheses, colon. New line, file, open quote, stdin command, end quote, comma, line 1, comma, in module. New line, type error, colon, unorderable types, colon, students in empty and empty parentheses, left arrow, student, empty parentheses. As you can see, Python gives us an error message. We have a type error message because it does not know how our student objects should be ordered. If you think about it, that makes sense. We've not defined any implicit ordering for students, and we might want to arrange them in different order for different purposes. In this example, we want them ranked by GPA. In another context, we may want them in alphabetical order. In data processing, the field in which records are sorted is called a key. To put the students in alphabetical order, we would use the same as the key. No, we would use the name as the key. Sorry, that was misread. For our GPA problem, obviously we want the GPA to be used as the key for sorting the students. The built-in sort method gives us a way to specify the key that is used when sorting a list. By supplying an optional keyword parameter, key, we can pass along a function that computes a key value for each item in the list. For example, list.sort, open parentheses, key equals key underscore function, end parentheses. The key underscore function must be a function that takes an item from the list as a parameter and returns the key value for that item. In our case, the list item will be an instance of student, and we want to use GPA as the key. Here's a suitable key function. Def use underscore GPA, parentheses, a student, end parentheses, colon, new line, return a student dot GPA, empty parentheses. This function simply uses the GPA method defined in the student class to provide the key value. Having defined this little helper function, we can use it to sort a list of students with call to sort. Do I have to read this out? You should read this in your book. We have self pip 4, self pip 5, self pip 6, self pip 7. Recall that underscore underscore make pip is a local method of the die_view class that creates a circle centered at the position given by its parameters. We want to replace these lines with code to create a list of pips. One approach would be to start with an empty list of pips and build up the final list one pip at a time. I am not following. Oh, I think I missed a page. I did. So from page 377, the list of students with call to sort, data.sort, parentheses, key equals use underscore GPA, end parentheses. That makes a lot more sense now. On page 378, chapter 11, data collections, new paragraph. An important point to notice here is that I did not put parentheses on the function name, parentheses, use underscore GPA, empty parentheses, end parentheses. I do not want to call the function. Rather, I am sending use underscore GPA to the sort method, and it will call this function anytime it needs to compare two items to see what their relative ordering should be in the sorted list. It's often useful to write this sort of helper function to provide keys for sorting a list. However, in this particular case, writing an additional function is not really necessary. We have already written a function that computes the GPA for a student. It's the GPA method in the student class. If you go back and look at the definition of that method, you will see that it takes a single parameter, self, and returns the computed GPA. Since methods are just functions, we can use this as our key and save ourselves the trouble of writing the helper. In order to use a method as a standalone function, we just need to use our standard dot notation. Data.sort, parentheses, key equals student.gpa, end parentheses. This snippet says to use the function / method called GPA defined in the student class. I think we now have all the components in place for our program. Here's the completed code. Before I read this, I need a sip. Here we go. We have hashtag GPA sort.py. New line, hashtag, a program to sort student information into GPA order. New line, from GPA import student, comma, make student. New line, def, read students, open parentheses, file name, close parentheses, colon, new line, in file equals open parentheses, file name, comma, single quote, R, single quote, end parentheses. New line, student equals empty brackets. New line, for line in file, colon, new line, students dot append, open parentheses, make student, open parentheses, line, end parentheses, new line, in file dot close, empty parentheses, new line, return students. New line, def, write students, open parentheses, students, comma, file name, end parentheses, colon, new line, out file equals open parentheses, file name, comma, W inside single quotes, end parentheses, new line, 4S in students, colon, new line, print, open parentheses, open quote, 0 inside fancy brackets, \T, 1 inside fancy brackets, \T, 2 inside fancy brackets, end quote, period, new line, format, open parentheses, S dot get name, empty parentheses, comma, S dot get hours, empty parentheses, comma, S get Q points, empty parentheses, close parentheses, comma, file equals out file, end parentheses, new line, out file dot close, empty parentheses, new line, def, main, empty parentheses, colon, new line, print, open parentheses, open quote. This program sorts student grade information by GPA, end quote, end parentheses, new line, file name equals input, open parentheses, open quote, enter the name of the data file, colon, end quote, end parentheses, new line, data equals read students, in parentheses, file name, new line, data dot sort, open parentheses, key equals student dot GPA, end parentheses, new line, file name equals input, open parentheses, open quote, enter a name for the output file, colon, end quote, end parentheses, new line, write students, open parentheses, data, comma, file name, end parentheses, new line, print, open parentheses, open quote, the data has been written to, end quote, comma, file name, end parentheses, new line, if, underscore, underscore, name, underscore, underscore, equals, equals, single quote, underscore, underscore, main, underscore, underscore, end single quote, colon, new line, main, empty parentheses. Okay, see? So simple. Section 11.4, designing with lists and classes. Lists and classes taken together give us powerful tools for structuring the data in our programs. Let's put these tools to work in some more sophisticated examples. Remember the die view class from last chapter? In order to display the 6 possible values of a die, each die view object keeps track of 7 circles representing the position of pips on the face of a die. In the previous version, we saved these circles using instance variables pip1, pip2, pip3, etc. Let's consider how the code looks using a collection of circle objects stored as a list. The basic idea is to replace our 7 instance variables with a single list called pips. Our first problem is to create a suitable list. This will be done in the constructor of the die view class. In our previous version, the pips were created with the sequence of statements inside underscore underscore init underscore underscore colon. So here we have self dot pip1, we have self dot pip2, we have self dot pip3. I do hope you read this for yourself. Self dot pip4 is equal to, self dot pip5 is equal to, self dot pip6 is equal to, self dot pip7 is equal to. Recall that underscore underscore make pip is a local method of the die view class that creates a circle centered at the position given by its parameters. So whether it's offset, it looks like. We want to replace these lines with code to create a list of pips. One approach would be to start with an empty list of pips and build up the final list 1 pip at a time. Pips equals empty brackets, pip.append. I go ahead and read this. Pips.append, 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 self.pips equals pips. So we have the CX and offsets, and we have CY and offsets, and this is going to give the pips positions. An even more straightforward approach is to create the list directly, enclosing the calls to underscore underscore make pip inside list construction brackets like this. Self.pips equals in bracket. You're going to have to just read this. We have CX's and CY's positioning the pips inside of brackets. That's all I can tell you. Notice how I have formatted this statement. Rather than making one giant line, I put one list element on each line. Again, Python is smart enough to know that the end of the statement has not been reached until it finds the matching square bracket. Listing complex objects one per line like this makes it much easier to see what is happening. Just make sure to include the commas at the end of the intermediate lines to separate the items of the list. I can clearly see the commas up above. The advantage of a pip list is that it is much easier to perform actions on the entire set. For example, we can blank out the die by setting all of the pips to have the same color as the background. For pip in self.pips: pip.setFill self.background. See how these two lines of code loop through the entire collection of pips to change their color? This required 7 lines of code in the previous version using separate instance variables. Similarly, we can turn a set of pips back on by indexing the appropriate spot in the pips list. In the original program, pips 1, 4, and 7 were turned on for the value 3. Self.pip.1 No, self.pip1.setFill, self foreground, self.pip4.setFill, self foreground, self.pip7.setFill, self foreground. In the new version, this corresponds to pips in positions 0, 3, and 6, since the pips list is indexed starting at 0. A parallel approach could accomplish this task with these 3 lines of code. Self.pips 0 in brackets dot setFill self foreground, self.pips 3 in brackets dot setFill self foreground, self.pips 6 in brackets dot setFill self foreground. Doing it this way makes explicit the correspondence between the individual instance variables used in this first version and the list elements used in the second version. By subscripting the list, we can get at the individual pip objects, just as if they were separate variables. However, this code does not really take advantage of the new representation. Here is an easier way to turn on the same 3 pips. For I in brackets 0, 3, 6, colon, new line self.pips I in brackets dot setFill in parentheses self.foreground. Using an index variable in a loop, we can turn all 3 pips on using the same line of code. The second approach considerably shortens the code needed in the setValue method of the DieView class. Here is an updated algorithm. Loop through pips and turn all off. Determine the list of pip indexes to turn on. Loop through the list of indexes and turn on those pips. We would like to implement this algorithm using a multi-way selection followed by a loop. For pip in self-pips, self.pip.setFill self-background. If value equal 1, colon, on equal 3 in brackets, if value equal 2, colon, new line on equal 0 or 6 in brackets, 0, 6. If value equal 3, colon, new line on equal 0, 3, or 6 in brackets, if value equal 4, colon, on equal in brackets 0, 2, 4, 6, new line if value equal 5, colon, new line on equals in brackets 0, 2, 3, 4, 6, new line else, colon, on equals brackets 0, 1, 2, 4, 5, 6, new line for I in on, colon, new line, self.pips, I in brackets, dot set fill, open parentheses, self.foreground, end parentheses. The version without lists requires 36 lines of code to accomplish the same task, but we can do even better than this. Notice that this code still uses if, elif structures to determine which pips should be turned off. Since the correct list of indexes is determined by value, a number between 1 and 6, we could make the decision table-driven instead. The idea is to use a list where each item is in the list, it is itself a list of pip indexes. For example, the item in position 3 should be the list 036, since these are the pips that must be turned on to show a value of 3. Here is how a table-driven approach can be coded. Okay, I'm going to pause here and come back to this, page 382 in chapter 11 later. I've run out of time. I'll be back later. Bye.